Ever notice how ideas never stand alone? It's like this tower here. Every idea is built on the shoulders of something else. Some of the pieces might not matter very much. We can take them or we can leave them. But others, like these blocks on the bottom, they're basic. If you move one of these, see what I mean? Noah's flood is like this. For people who have built their faith in God around the Bible, its historical accuracy is very important. If the flood wasn't real, then our tower's in trouble. But things don't have to come crashing down like this. There's important evidence that Noah's flood stands on solid ground, and that's what we want to show you. Do you know the story about Noah and the ark?
Mm-hmm.
Do you believe it ever happened?
You would like to think it, just because you've been brought up with thinking it.
I guess I should believe what the Bible says, yes.
It could have rained a lot. God could have gotten mad.
No one could have made it up that well. It's difficult making up a strong story like that.
I'm not certain of it, no, but I think that perhaps it did occur, and it's a possible explanation for things that other people would attribute to evolution.
I believe it could have happened because there's so many things that's phenomenal right now that has happened that it's hard for us to digest. So why could it not have happened?
Do you believe it ever happened?
Yes.
What makes you believe that?
My family bloodline goes to Noah.
I gotta believe something. It says so in the Bible.
Without a doubt, Noah is the most famous sailor in history. He and his boat have been used in a lot of different ways to tell a lot of different stories. But Noah isn't the only flood hero we can choose from. Many different flood legends have been discovered with many different characters. They were famous in their day too, long before the Genesis account was even written down. A lot of these stories sound familiar. In fact, there's so many similarities, you might think they're describing the same event, and that may be. But written accounts can never prove the flood actually happened. To be really convincing, we need something a little more concrete. Hey, up here! The best kind of evidence comes from places like this, the rocks. The most important rocks are ones like these. They're called sedimentary or stratified rocks. Strata for short. You always find strata in layers like you see here, all different. Different colors, different texture. Some came from different places. These differences give us a kind of picture of the past. Going up a stack of sediments like this is kind of like turning the pages of a history book. Of course, the language takes a little bit of getting used to. For instance, here we have some sandstone. Now we know that sandstone is made when sand is cemented together with minerals or pressure. Now, this next layer, just below the sandstone, is shale. It's usually formed on a lake bottom or off a coastline somewhere. A lot different than the sandstone layer above. In order to get these very different rock layers together like they are here, some big changes had to take place. Shale is made of very fine sediments that settle out in quiet water. Sandstone, on the other hand, is coarse and granular and could come from a number of places, like a desert, for instance. So maybe in this place was once a quiet lake, and later perhaps a dry, sandy plain. Every one of these layers tells a story just like that. We can find deserts, oceans, volcanoes, their time and place all faithfully recorded. With such a trusty accounting system, there's no way a big event like Noah's flood could happen without leaving its mark, here, in the rocks. Especially when you consider how the record was made in the first place. What we know about the Earth's past we owe for the most part to water. Rain, to be exact. 30,000 cubic miles of water falls in the land every year. The biggest part soaks into the ground or evaporates, but about a third runs off into rivers and lakes, and in the process carries off more than 20 billion tons of sediment at the same time. We've all seen what muddy water looks like. It's the sediment mixed in that gives it its color. As long as the water keeps moving around, the sediment stays mixed. But as soon as it stops, the sediment settles out and forms a layer right there in the bottom. River deltas are made that way. This is pretty much how the sedimentary rocks were formed too, but on a much larger scale. Higher areas, like hills and mountains, are worn down by weather, rain, ice, what have you. The bits and pieces washed off are dropped in a lower area, like a valley or a lake, and settle out. Now we call that sediment. This erosion that grinds away at the mountains is a continual process, but the transport system downhill isn't. So the sediments don't come in one continuous flow, but rather in intervals, which means that instead of a single even deposit, we get layers, like this. Washed down along with the sediments are all sorts of other things, depending on how much water you have. Leaves, animals, insects, or even fish, like this one. You can find a slice of life from the time buried in the mud. If the layers get thick enough and the right chemical interactions take place, the mud is transformed into rock. The sediments and the traces of life buried in them are preserved. Eventually, some of these layers get pushed back up again into mountains or hills. Water starts in again, wearing away at the surfaces. New layers may form and old ones are uncovered. Once these are out in the open again, we can look inside and see what went on in the past. If we're going to learn about the past, the strata is our key. But of all this land out there, there are only a few places where the strata is opened up like this so that we can see it. The best one is over here on the northern border of Arizona. It's a place called the Grand Canyon. The Grand Canyon. It stretches for 270 miles along the Colorado River. 18 miles across at its widest point. It reaches almost a mile deep in places. But numbers can't begin to convey the spectacle of the largest canyon in the world. The Grand Canyon offers not only incredible beauty, but also startling evidence of the work of nature. To stand at the edge and look below is to take in an expanse of rock representing a major part of Earth's history. To most geologists, the colored layers tell of tropical seas, high deserts, swampy lowlands, and sluggish rivers. The canyon follows the course of the Colorado River as it winds south to the Gulf of California. You can see the erosion all up and down here. A few billion tons of real estate just washed away. But as good as it is, the Grand Canyon gives us only a part of the picture. For more, we have to keep on going, about 100 miles further north to a mountain called Brian Head. From the top of this mountain, all the way down to the bottom of the Grand Canyon, we've got one of the most complete geological sequences in the world. You can see how it works better here. We've taken out a slice of the canyon up to Brian Head and simplified it a bit. Here's the canyon, and up here is Brian Head. The whole area is part of a huge uplifted section of ground called the Colorado Plateau. Rising out of this plateau is the Grand Canyon, its northern rim being more than 1.5 miles above sea level. At the bottom here, we can find some of the oldest sediments known. Coming up the walls, we see later deposits piled one on top of the other. Now, as we come up over the rim, you can see how the record keeps on going on back and up towards Brian Head. At the very top here, we have some of the most recent deposits in the area.
We're looking at the Colorado River in the Grand Canyon. And when you look at this, one of the first thoughts that comes to mind is, could such a small river as this cut such a huge canyon?
Dr. Ariel Roth, director of the Geoscience Research Institute in Loma Linda, California, has studied the features of the Colorado Plateau for more than 20 years, and like many geologists, has struggled to explain this vast canyon.
There are many ideas regarding how the Grand Canyon was formed. There's no general agreement regarding it, but there are some suggestions.
Although no one knows exactly how the canyon came to be, a general history of the area can be reconstructed, which helps us better understand what we see today. In the beginning, the Colorado Plateau was a flat lowland plain. The earth was younger then, and the crust was pretty simple. This was ground zero. After a while, sediments started coming in and layers piled up one after another. These were pushed around, broken up, and gradually, erosion began wearing down the layers. Over time, almost the entire sedimentary record previously deposited was worn away. Over this bare rock, new deposits came in and more layers formed. These were also bent, faulted, and moved around. Again, erosion started wearing the layers away. Today, all that's left is a remnant of the thousands of feet of sediment that were originally deposited. What makes this such a gold mine for geologists is the way the sediments were tilted by this uplift here. The layers were raised and then cut across at an angle, giving us a much wider view than we would have had otherwise. More than 23,000 vertical feet of sediments are all exposed here, spread out across about 100 miles of desert, a big chunk of Earth's history, all right here in one spot. Here in the Colorado Plateau, we have the concrete evidence that we've been looking for. This is one of the most complete records of the past that we can find anywhere. And for some pretty good reasons, we think that the flood is written all over it.
Birds all in a row, two are baby chickens, a third who knows.
A favorite children's game is trying to discover which thing doesn't fit in. It's a good game and good science too. Earth scientists do the very same thing, only they are looking at maps and computer printouts instead of baby birds. To a scientist, finding something that doesn't fit can be very useful. But poor fits can also cause problems, especially when you can't figure out why they don't fit. Take this for instance. Shells, bivalves to be exact, they're somewhat similar to our clams of today, buried in a formation that's roughly the size of the state of Utah, full of shells, yet 800 miles from the nearest ocean.
We're looking here at the Carmel Formation. Carmel Formation is a Jurassic formation. It's a complex formation, actually, extremely widespread. Runs from here clear up into Canada. Probably at least 200,000 square miles of Carmel. We have deposition here on a scale that is completely different from anything that we see going on the surface of the Earth at present.
This rock represents one of the big puzzles in geology. These kinds of rocks, made up of ocean sediments, are by far the most common type of sedimentary rock there is. There's more ocean strata on the land than there is land strata on the land, and that's a problem. How did all this ocean sediment get all the way up here? A piece of wood floats on water because the water is heavier, more dense than wood. Rocks can behave the same way. The basement rock that forms the ocean floor is more dense than the rock that makes up our continents. The lighter continental rock actually floats on top of this basement layer, keeping our heads above water, so to speak. But all those marine sediments suggest it might not always work that way. In fact, what is land today might have been oceans in the past. Scientists believe that for some reason, and no one really knows why, the continents started sinking. We can't be sure just how fast or how far this drop was, but at one point the continental rock dropped at least 10,000 feet below its present level. Seawater and ocean sediments covered the land areas. Later on, the theory goes, the continents rose back up, leaving these ocean sediments high and dry. This switch was no fluke. It apparently happened several times. Marine formations can be found all throughout the Colorado Plateau. In fact, there are at least 6 major ocean deposits which are sandwiched in the record here. To account for all these sediments, geologists believe this kind of thing happened at different times in different places. Taken together, the continent appears to have been underwater more often than it was above. Sinking continents could explain how marine deposits could be found on dry land today, like we see here in the Grand Canyon. But on the other hand, marine sediments are just the kind of thing that we might expect from an event like Noah's flood, and maybe for the same reasons. If oceans and land areas can trade places like this, then it could have also happened during the flood. But instead of several cycles, we'd be looking at only one, and a fast one at that. It would have put shells in the most unlikely places.
A great deal of the Alps are limestones, and they're pushed up now, and we find all the ammonites and all the other mollusks, we find them high in the mountains. So for somebody who is not much into geology, it's a surprise to find those fossils up in the mountains. And I personally think that are evidence of a flood.
The truth is, no one's ever seen a continent underwater like this. All we've got are the shells to go on. And whether the shells were brought here by sinking plates or by a global flood, or both, marine deposits on the land tell us that at some point, somehow, the oceans covered the land. And that's a lot like the Bible's description of the Genesis flood. About 70 miles due east of the Grand Canyon, an unusual rock formation called the Chinarup Conglomerate has been uncovered.
The Chinarup is an unusually widespread and unusually thin rock formation that we find here in the western United States. It is only about 90 feet thick, yet it runs over an area of 100,000 square miles.
The Chinarup Conglomerate covers the greater part of northern Arizona, Utah, western Colorado, and New Mexico. Most geologists agree that this extensive formation was deposited by water, like a river or a lake, but just how this was done is still not well understood.
When you look at sediments and so on, you can tell to a certain extent what type of environment they were deposited in. Now, it's not always easy to do this, but the Chinarup is so unique, it's fairly easy to say that it was not a lake deposit. A lake deposits very fine silt, clay, and a very even type of pattern. You look at the Chinarup, the pattern is not that even, and the sediments are very much coarser. It's been suggested sometimes that the Chinarup was deposited by river deposits, but it strains your imagination to think that a river would be depositing material over 100,000 square miles in such a thin type of layer. This is not the type of deposits we get from river at all. This wasn't a river or a lake. This was a catastrophe.
One explanation for the Chinarup suggests that a huge flood washed over highland areas, sweeping rock, sand, and plant material into a wide basin. This debris settled out evenly over a large area, leaving the extensive deposit we find today.
100 feet probably beyond that. It's still big there. And you look down here at some of this.
The most important evidence for the flood idea comes from fossils. Both the Chinarup and the Chinle Formation above it have an abundance of petrified wood mixed in with coarse, rocky sediments, material that was certainly washed in from other areas. A flood of this size would be hard to imagine today, but it appears they weren't as unusual in the past. A number of these widespread deposits can be found in the record.
The Schnarp is not the only deposit like this that we find. As we look through this region, just the western United States here, we find extremely widespread deposits, some of them larger than the Schnarp. Just above the Schnarp, we got the Cheney Formation, which is spread around for 175,000 square miles. And then you get to the Dakota Formation, which is not quite that unique. But that thing goes from this region here around the Grand Canyon clear on up to the Black Hills of South Dakota. And on top of that, we have the Morrison Formation, which is characterized by dinosaurs. It has lots of dinosaurs in it. And that thing spreads over 400,000 square miles. It runs clear from Texas on up to Canada. And in the metric system, we're talking about over 1 million square kilometers for the Morrison Formation.
All of these formations have been explained in different ways, but the most common is local floods or some other kind of water activity, but always on a relatively small scale. However, these kinds of widespread water-formed deposits could have been made another way.
It is extremely difficult to conceive of local activity being so uniform and so widespread over such wide areas such as where we find these formations. But these kind of unique deposits are just the thing we'd expect in a worldwide flood such as described in the Bible.
With water covering the continents, sediments could have been easily deposited over wide areas. In addition, very different types of sediments from different places could be deposited together, one on top of the other. Widespread deposits of unusual sediments have been discovered on every continent. They are evidence of water activity on a much larger scale than anything we see today, but just the kind of thing we'd expect from an event like the Genesis flood. The invention of the teletype and later the telephone made our world a much smaller place. Visionaries told of how one day the whole world would be bound together by these inventions. And people were listening. A major hurdle was cleared when, after years of failure, submarine, telephone, and teletype cables were stretched across the Atlantic, connecting North America to England. It was an engineering feat without equal at the time and set the stage for one of the most important discoveries in modern geology. November 18, 1929, a little after 3 in the afternoon, the New England coast was shaken by a powerful earthquake. It was centered off the coast of Newfoundland, Canada, right on top of the busiest submarine cable network in the world. In this part of the coast, the continental shelf extends several hundred miles out from shore. In 1929, 13 submerged teletype cables crossed this point here. Now, 8 of the cables were higher up on the shelf than the others. They were broken instantly, probably by the initial shock of the quake. Further down the slope of the continental shelf, 5 more cables had been strung. Over the next several hours, these cables were snapped one by one in order from top to bottom, like some giant hand reached out and swept them off. All sorts of ideas were proposed to explain it, delayed stress and strain, what have you. But in 1952, a couple of scientists discovered the giant hand idea wasn't such a bad comparison after all. The cables had been broken by a turbidity current. You can think of a turbidity current as some kind of underwater avalanche. They're a lot the same. They almost always start near the mouth of rivers where a lot of silt and sediment build up. From time to time, when these deposits get too heavy, or maybe there's an earthquake, they break loose and begin to slide. At first, it might look like the moving sediment would mix in with the water above it and float away in a cloud of muddy water, but it doesn't. When sediment is thoroughly mixed with water like this, it takes on properties all its own. The mixture is heavier than the clear water, and when it breaks loose, it stays together in a unit, flowing underneath the lighter water in the same way water flows under air. And it can flow about as fast, too. Even on very gradual slopes, turbidity currents can reach speeds of more than 60 miles per hour. So in a very short time, these flows can spread sediment over a very wide area. These kind of underwater deposits are called turbidites. In the Grand Banks earthquake, a mass of sediments on the edge of the continental shelf broke loose. The slide formed a turbidity current that swept down the continental slope to the ocean floor, snapping cables as it went. When the flow finally came to rest, it had dropped about 2 feet of silt over 40,000 square miles of seafloor, all in about 13 hours. We can find turbidites here in the record too. We know them because all turbidites have certain features in common.
Okay, we're looking here at a rather typical turbidite. If you look at this layer carefully, you can notice it's divided into two parts. We have a coarse part here and a finer part here. You look at the coarse part, you notice it's coarser down at the bottom than it is up here. This is the graded portion of what we call a turbidite, while this represents the fine portion of a turbidite. Now, turbidites, some of them are much more complex than this, sometimes have as many as 5 different units in them.
Since most of the record was deposited by water action, we could expect to find turbidites in it. And we do, lots of them. In fact, there are so many turbidites that they've sparked kind of a revolution in geology. We don't know what to do with them all.
In the rock record, on land, we find many turbidites. You can recognize them by the grading of the sediment. Coarse grains at the bottom and fine grains at the top. Probably 30% or even more of all the sediments that have been deposited in the past were deposited as turbidites.
Turbidite concept is it's a new concept in sedimentology. It's been in vogue only for about 25 years or so, but it has completely revolutionized some of the thinking as sedimentary layers are analyzed. Tens of thousands of layers that were originally thought to have been deposited very slowly in shallow seas over long periods of time are now interpreted as being deposited by turbidites very rapidly. This whole thing was deposited more or less instantaneously. This new concept of turbidites reflects the general trend in geological thinking towards interpreting things more in terms of catastrophes than in terms of slow processes going on over very long periods of time.
We saw before that sedimentary rocks were formed when sediments suspended in water settle out and form layers. Under the right conditions, these layers turn to rock. Now, judging by what they see today, geologists thought that these sediments would require hundreds, maybe thousands of years to pile up like this. But the discovery of turbidites changed all that. Geologists have gone back and found many of these layers are really turbidites. So instead of being evidences for long periods of time, they show rapid action requiring days instead of centuries. Things were happening back then a lot faster than we thought. Just like the shells we found in the desert, having so many turbidites on the land can be a problem. Turbidites are formed underwater and under special conditions, not the kind we generally find on the continents today. But turbidites, like shells, are just what we'd expect to find after the Genesis flood. With water covering the continents, great currents could have piled sediments together in heaps. From time to time, these would break loose and form turbidity currents. In this way, thousands of sediment layers seen in the record today could have been made very quickly.
Talking about turbidites is talking about fast sedimentation, and that's the thing we need when we're talking about the flood. Talking about turbidites, we are talking about deposits which can reach an area of about the size of the Netherlands. And what's even more amazing is that they are uniformly thick. So they may be a couple of meters, but they may also be 200 meters thick. So we're talking about a massive kind of sedimentation, which in my view is a catastrophe.
How these conditions came to be on the continents is still anybody's guess. However, one thing is clear. A great portion of the sediments on the continents were deposited quickly and underwater, just the kind of thing we'd expect from a worldwide flood. Things aren't always what they appear to be. For instance, I can make it look like this little handkerchief just disappears. But of course, it really isn't gone. It's just an illusion. We have the same thing happening in geology. The sedimentary layers that we see in the Grand Canyon appear to be an orderly record of the past, but they aren't really. Big gaps of time exist, blocks of the record that have just disappeared. We know that isn't possible, so what happened to the record? We saw before that layers are made because the sediments are deposited in intervals. When a new layer comes in, we can see a line of separation between it and the older layer below. This line is important. It represents the time that passed between when the bottom layer was laid down and the next layer came in on top. Could be a few hours or days, even years. Nobody knows for sure. It's quite possible the lines between the layers represent far more time than the layers themselves. We can narrow down the interval by looking for certain clues. For instance, erosion. It probably worked in the past about the same as it does today, grinding away at the planet's surface. It's one of those constants that you just can't escape. So if a sediment layer were left exposed for any amount of time out here, we'd expect to see some erosion taking place, like we see today in the Grand Canyon. Ruts, gullies, that sort of thing. The longer it was out in the open, the more erosion we should get. The only thing that would stop it would be if later on a new layer of sediment came in on top. The cuts and gullies in the lower layer would be filled in by the new sediment coming in, but the uneven surface would be preserved as a ragged contact. Everywhere we had a break in the process for an extended time, we should see this kind of erosion between the layers. If, on the other hand, the contact line between the two layers was straight and even, like this, then we could be pretty sure we're looking at a short period of time. The next layer covered up the first one before erosion had a chance to wear it away, so the contact would be flat. Everywhere we see flat contact lines, then, we know we're looking at some pretty fast action by geologic standards. This is what we might expect, but it isn't always the case.
You are looking here at the contact between reddish layers above, and below it we have some slightly grayer, shaly layers. Between the two is one of these so-called time gaps. It represents a gap, according to some interpretations, of 100 to 150 million years. And we would certainly expect a lot of irregular erosion at that time. Yet you notice here that the contact is very flat. There is a little bit of erosion, and you can see it right here, but the erosion is very slight compared to what we would expect over such long periods of time.
Time gaps, like this one between the red wall and the mauve limestones, are estimated by comparing strata in the different parts of the world. The order of sediment layers is not the same everywhere you go. Sometimes sediment layers found in one place are missing in others. When this happens, the gap left in the record represents not just the lag between deposits, but the time in the missing layers as well.
Between that top layer, which is the tannish cliff former, and the reddish and whitish layers below, we have what is assumed to be a 12 million year gap. However, it looks like that gap never did take place because you have a very flat contact line. If those lower layers had rested there for 12 million years, we would expect a lot of erosion, such as you see in the hillside below.
A number of these time gaps can be found throughout the Colorado Plateau. In this area alone, more than 200 million years are gone without a trace. In almost every case, the contacts are remarkably flat, showing little, if any, evidence of erosion. To account for these unusual features, geologists have offered two possible explanations. First is that erosion took place more slowly in the past. Perhaps there was less rainfall or the climate was different than today. That's why a layer of sediment could lie around for 10 million years without looking like it. The second way is that the missing layers were deposited, but were worn away before the next layer could come in on top. The contact is flat because this wasn't your run-of-the-mill erosion going on here. Instead of cutting canyons like we see today, the whole surface was worn down evenly. No gullies, no ruts, just a flat, even surface. The new layers coming in drop down on a smooth, level plane. We don't see this kind of erosion today, especially on such a large scale, which has led some scientists to propose an alternative view.
It looks as though these layers were laid down very rapidly, one on top of the other, as we'd expect during the worldwide flood, and that this so-called 12 million year period never occurred. In the model of a flood, we expect the layers to have been laid down rapidly, one on top of the other, and you have the evidence there that seems to suggest that.
If the time gaps we see in the record aren't really gaps at all, then the geological time scale changes too. A sediment layer could be deposited in one part of the world, while at the same time another layer, considered much older, is being deposited somewhere else. This kind of doubling up is just what we would expect from a global flood. With water covering the whole land, it would be very easy to get deposits of many different types laid down in different places at the same time, and do it very rapidly. Currents in source areas, not time, would determine to a great degree the order in the record.
As we look at the evidence, such as the abundance of turbidites on the continents, the abundance of marine fossils in the sedimentary layers on the continents, when we look at the extremely widespread depositional environments over hundreds of thousands of square miles, when we look at the lack of erosion between layers, I think we have fairly compelling evidence that these were laid down during a worldwide catastrophe such as the flood described in Genesis.
One of the best ways to find out if your ideas are on the right track is to test them. When you do, you discover which ones work and which ones don't. But that's not always easy to do. Some things are too big or too small to get our hands on. In cases like that, we make what's called a scientific model.
Well, a scientific model is it's an explanation, really. How does something really work? And so I try to figure out how I think it works, and I call that a model. Sort of like building a model airplane. It's not a real airplane, but it represents a plane as well as you can. And the same way in my mind, if I try to figure out how something works, why, I call that a model.
Some models are pretty straightforward, like this airplane, for instance. But when you're dealing with models of the past, things get harder to pin down. A wood or plastic model could never represent the forces that shaped our planet. We have to build this kind of model in our minds. Scientists compare what we see going on today with what appears in the strata. From this, they reconstruct what they believe the past was like. Many times, these models are only guesses, but they provide a reference point from which to start. Uniform conditions, gradual change, and long ages make up one model of the past. Noah's flood is another. Let's take a closer look at how the model of Noah's flood can help explain what we see in the rocks. The first thing we've got to do is to get away from the notion that Noah's flood was some big rainstorm. The tremendous upheavals recorded in the rocks are evidence of a destructive event almost beyond imagination. It may have rained, it's true, but that was only the beginning. We really don't know much about what the earth was like before the flood. We only have a few brief descriptions in Genesis, just enough to give us some general ideas. The continents and oceans were probably arranged very much like they are today, the lighter crust floating on the more dense basement layer. Both land and sea supported all kinds of plant and animal life. We could probably have found specific habitats or life zones similar to those we have now. Deep ocean, tidewater reefs, coastal plains, inland forests, even alpine meadows. In fact, it could be reasonable to assume things were much like they are today, only more abundant. One very important detail about the pre-flood Earth we do have was that it didn't rain. The Bible says the land was watered by a mist from the ground. Now what this was, we can't tell from the description, but you'd have to have a lot of misting to support all the plant and animal life there. In our model, we'll supply the water through a network of underground lakes and streams. We'd call them aquifers today, the kind of water deposits well drillers look for, only these would have been a lot bigger. Just what caused the flood we may never know. What we do know from the Bible is that it rained and that the land areas were covered with water. But rain alone, even 40 days of it, couldn't account for what we see in the record. The fountains of the great deep were broken up, the Bible says. Water came from other sources as well.
Well, the only place you're going to get water like this quickly is from the ocean. And for that to happen, we would have to have a change in the relationship between the ocean and the land. Now, there's plenty of evidence for this. You go through their geologic record, you see a lot of marine deposits on the land, so we know it's happened in the past. But the difference here for the flood is that it would have had to have happened a lot faster than anybody ever thought. So to model it, we decided to try and animate it, to take the action that we think should happen and put it together in a moving way, and then we can see the action. We can then critique it better.
Shortly after the rain began, the crust started to sink, and pretty fast too, creating some major stresses in the crust. The underground aquifers, pressed by the collapsing crust, would have burst through, adding to the water above. With a drop in land level like this, the seas would have poured in. Today, a medium-sized earthquake along the coast can create some good-sized tidal waves, but these are just ripples compared to what must have followed there.
I don't think anybody has a good explanation for what would make the continents behave like this. But that's not unusual. I mean, if you look at the geologic record, most of it's a big question mark anyway. But when you look at it in terms of the flood, then it all starts making sense.
Once the land was covered with water, different kinds of sediments could have been shifted all over the place. Marine sediments from the seafloor were washed over highland prairies. Turbidity currents from inland areas swept across what had once been the seacoast. The ash and lava from volcanic eruptions mixed in here too. During the course of the flood, the building blocks for a number of different rock types were piled one on top of the other. By the time it was over, these layers could have stacked up several thousand feet. After a time, the continental rock began to rise back up. As it rose, the crust would have buckled in places. Mountain ranges rose from these folds and were shaped and reshaped by the water pouring off the land. Great quantities of water were trapped and formed inland seas. Others broke through and cut magnificent canyons, washing huge quantities of sediment off the land, dumping it hundreds of miles away. And then, after a relatively short period of tremendous upheaval, the dust began to settle, leaving behind a record we have only just begun to understand.
I think the flood model probably is the best model that I know of at this point. I see that a flood model can answer, to my satisfaction, a large amount of the data that we see in the field.
Ideas never stand alone. We have to build on what's gone before. In history and in science, if you build your faith on the Bible, that's one tower that's never going to fall.